Okay, according to my watch. And so we have to start our session. It was a great privilege and pleasure for me to introduce talk which will be delivered by Professor Bruno Coppi about, let us say, plasma effects around supermassive black hole. It's very important issue, and importance of this issue is increasing in the last years due to new observational data. Please, Professor, 35 minutes for talk and 5 minutes for questions and discussion. Thank you.
Well, thank you very much for your interest in this subject and for inviting me. In fact, I'm interested in your comments to what I have to say. Let me start something that you already know from very long time ago. In 1967, the Institute for Advanced Studies decided to start a new school. They used to have mathematics only. And so they invited some physicists who had connection with the experiments in order to. So they invited Marcel Rosenbluth and me and another person to start activities in plasma physics. And as soon as I joined, on the same floor, I found that Tullio Regge was a mathematical physicist, a wonderful person. And we began to discuss. And then Johnny Wheeler would begin to visit us. At first, he used to work with Regge, but then he discovered that I had worked in plasma physics, he had worked on the hydrogen bomb, and then he immediately drafted me to his interest. So we all concluded, Regge, Wheeler, and myself, that if black hole had to be physical object, they used to be considered in those days mathematical objects, there had to be matter around them. It would not be right to study them only. And I'm glad that Professor Zakharov mentioned that there is growing interest because it is not natural to consider black holes surrounded by vacuum. So many years went by and I kept that interest I went to MIT because I was invited by Professor Rossi who had started X-ray astronomy there. At Princeton, there were nothing going on in space. And in fact, you may remember that black holes were discovered, in fact, by people that belong to the Rossi group out of the radiation emission due to the plasma surrounding them. And actually, these two people who discovered that they remain quite unknown, basically. Now, only one of them is getting recognition, but it is a very important step. As for myself, I set up an experimental program called Alcator that we use Russian ideas, but it went beyond technologically to find the same plasma that were expected to be around black holes. So they were about plasmas with density of 10 to the 15. And we did that. But by the time the experiment gave result, it became important for fusion research. And nobody really cared about the black hole aspects. Let me say that in those days at MIT, Ray Weiss, who had come from Princeton too, and I did not find much interest in general relativity. Now it is the other way around. It's all general relativity and zero plasma physics and so on. So let me now go into the subject. Okay. Now, what I found some time ago, that if you have a pair of black holes, or for example, only one with, let's call it a shepherd planet, something that modulates the gravity, you can sustain plasma modes that are intrinsic. They are parallel to the gravitational waves. And you don't need to introduce anything. They generate their own magnetic fields, not too much, I will show you. And there could be several categories of these modes. The first type of modes, they are localized around the vertical axis. That is, their plasma oscillation with frequency about the same frequency as the orbiting frequency of the binary. And they are not traveling waves, they are standing. So these modes are composed of a series of standing modes that are standing in the vertical direction. A standing mode is made of a propagating wave vertically in one direction and another one in the opposite direction, and they have equal amplitude. But then as time went on, I realized that you can get higher frequency modes by resonating with an intrinsic plasma frequency. And the case that we discussed today is that the resonance with the so-called ion sound wave. It's a kind of sound wave quite different from the acoustic waves that people know, which does not involve an adiabatic equation of state, but a isothermal equation of state, where the temperature fluctuations are really negligible. But as soon as you look at that, then I found them, as you will see. You need a mechanism to excite them. And of course, the periodic oscillation of gravity is an excellent driving factor. There is a large amount of energy associated with that. So basically, what I will discuss today is that the binary will launch a pair of waves whose frequency is a multiple of the orbiting frequency of the binary. These waves are coupled. They're not quite wave because they are modulated in amplitude, so that the nonlinear coupling is rather difficult, but it works. And so basically, I think this could be the seed for launching a beam out of this binary. Now, I will consider for simplicity the case in which the black hole binary is made of two equal masses, for example, 30 solar masses, as we are accustomed to think. But this process would work if we assume, like you do in planetary physics, that you have a single black hole, but you need to have a shepherd planet, like you have shepherd satellites around planets, that modulates the gravity. There is another way to excite these modes, is that by mode-particle interaction, we will consider that, and due to high-energy particle, for example. In this case, they would have the unpleasant role to take the high-energy particle and degrade it to low energy. That might be perhaps an explanation of why the binaries that have been discovered by their emission of gravitational waves, they're not seen actually in the electromagnetic spectrum. But most of us think that it is a question of resolution, that one day there will be electromagnetic emission associated with the collapse of a binary. Now, these pairs can be considered like gravitational phonons. You know, there's a certain type of collective modes, even though they don't strictly require knowing quantum mechanics, they can be described like quasi-particles. So we define a big H, which is not the H of quantum mechanics, but the energy and the momentum are related to this H, like in quantum mechanics. So you can imagine to have a scattering of these two phonons by the black hole gravity, and this is how they are launched. They are launching the same direction, only one side, because they could be launched also in the opposite direction. Now, as I said before, the frequency of these pairs are multiple of the gravitational potential oscillation frequency. But the wave, they rotate in the toroidal direction, and the rotation frequency is equal to the rotation frequency to the orbiting frequency of the binary. Now, the wave amplitudes, there are two types of amplitudes to consider. One is the, let's call it the electric potential, and the other one is the density oscillation. Now, there's the feature that the density oscillation, they peak within the height of the plasma disk, and they extend also in the halo region. While the amplitude of the electric potential tends to be steady, that is not decaying with the density. So it means that these waves are propagating also in the region where the plasma density is extremely low. And this is why they're very interesting. They don't die of the disk. Now, the pairing of this wave is treated as a nonlinear coupling driven by the fluctuating vertical force. In other words, the orbiting of the two black holes give rise to oscillation of the vertical force that attracts the plasma toward the horizontal plane, z equal to 0. Now, as I mentioned before, the phase velocity of one of these two interacting modes is equal to the so-called ion sound velocity. When we consider plasma disks where the electron temperature is considerably higher than those of the nuclei. Now, this model is being taken by the people working with the M87 black hole, those that produce that beautiful picture. Now, the other, the frequency of the other modes differs from that of the oscillation of the gravitational potential. And perhaps this is the way in which one day they will be discovered. There should be electromagnetic emission, and where of course, this wave would be able to penetrate to the plasma of the heliosphere only if their frequencies, they begin to be in the megahertz, which will not be easy. And if it could be possible to distinguish a difference of frequency by, let's say, 150 hertz or something, they could be revealed directly, but I doubt it. But the main effect of this mode is the so-called mode-particle interaction. They can be described very easily by quantum mechanical models, but they're quite different from the well-known Landau damping, because the spatial structure of the mode is not quite that of a mode. There is a combination of propagating wave with what we call ballooning modes. They were introduced by myself and Rosenbluth, in fact, years ago, before we joined the Institute. So let me begin to go a little bit in the mathematics, and then we can discuss. Now, let me say, since we have to put together gravitation and plasmas, we have to use quantities which are important for both. Now, the gravitational potential, is composed of a part which is due basically if you have two equal masses, which is steady state, and which is due to the sum of the two masses. We consider them to be equal. And then in addition to that, as you know, it's steady, it's axisymmetric. So it depends only on two dimensions, R and Z. I'm using cylindrical coordinate that is r, z, and phi. The oscillatory potential, as you go far away, it becomes quite small, but it is very different from the steady state potential in that it is 3D and it is not stationary. I will show you remind you what the ratio of this potential is. And then, of course, since electromagnetism comes in, you have to deal with electric potential and the magnetic vector potential. Now, something that all of you know very well is that we have to deal with half of the Schwarzschild radius, and here, then you have to consider the distance between the two black holes of the binary, and then we have to consider a distance that we call R0 of the active ribbon in the plasma disk, which we consider to be considerably larger than the radius of the last stable orbit. So we try to be in a region where Newtonian gravity is valid. But of course, we have to be careful about that because particles can be trapped by these waves and therefore they tend to go at the speed of light rather easily. Then there is another distance, which is well known in the physics of pulsar, that is the speed of light cylinder. Then another distance that is well known is the height of the disk. We consider to have a disk of high density, like the one that is well known for galactic black holes, for example, 10 to the 15 particle per cubic centimeter. And then it is surrounded by a halo, which is another scale distance, which is not listed here. Let's call it LH, which is much bigger than H. Then these plasma modes have a vertical wavelength. They are helical, which with a wave number which is K, and they have also a toroidal wavelength, which is 2 pi R0 over M0. In the case of a binary with two black holes of equal masses, as you know, M0, the lowest value of M0 is 2, which is the frequency you usually see. But in our case, we consider going up. And at first, I was hesitant to go up to, for example, M0 equal to 10, 20. But then I learned that in the case of galactic disks, I mean, people don't hesitate to go to this very high value of M, but they could be even higher. Now, we need to go to high value of M because the temperature fluctuation which are needed to couple these type of modes, they need to be rather small because of thermal conductivity relative to the density fluctuation. So we'll consider, let's say, M0s, which are 20 or something, 18, something like that, or more, of course. The higher, the better. Then there are several frequencies to consider. There is an orbiting frequency of the binary. Then if you are at R equal R0, there is a Keplerian frequency of the particle rotating around the binary. Then there is another equivalent frequency associated with the fluctuating potential. And then in studying with collective modes, you have to consider that there is an H bar. I will define what it is, which is the H bar equivalent of quantum mechanics, because this mode can be treated as quasi-particles. And in fact, when I was at the Institute for Advanced Studies, Rosenfeld and I wrote papers on that, using quantum mechanical methods basically to studying the interaction of plasma modes. So when we consider this plasma mode, consider the momentum and energy related by this type of quantity. Then there is an ion sound velocity, which is T, the electron temperature divided, well, there is an error there, divided by the mass of the nuclei. For simplicity, we consider the nuclei to be protons. And so this is the mass of the protons. Then there is the Keplerian velocity. There is a toroidal phase velocity of the mode. And then there is a vertical phase velocity, which is m0 times the orbiting frequency divided k. Now, the main dimensionless parameters are that the wave number of this helical wave vertical is much bigger than the height of the disk, they're rippled. And as you can see from any handbook, the ratio of the fluctuating potential to the steady potential is the distance square between the two black holes divided the radius square. I will find that the ratio of the fluctuating fields actually goes like the square root of that, so it is not too small. And that is why the nonlinear interaction is important. Now there's the summary again. Now let me consider some basic equation for the steady state part of the disk. We consider a flat disk. It could be corrugated. Then basically the equation for the confining the electric field that tends to push the electron out is compensated by the field exerted, gravitational field on the electrons, on the nuclei, and you can see that this equation is density independent. So it means that even when we go in the halo region, this equation is fine. Now the electric field is related to the plasma pressure in this way. Now, if you solve that equation in the case where the temperature T is independent of Z, you get a very well-known result. The density goes like an exponential like this. But in this case, the velocity, which is not a thermal velocity, but it is the ion sound velocity. Now, the sustaining factor of the confined hot electron population is this quantity, ENZ divided ZMI. So now when we go and consider the fluctuation, we will consider that this SF is modified and it will become equal to basically the square of the fluctuation frequency times the plasma density steady state. Now, this will be the square in the fluctuation amplitude. So it means that the fluctuation amplitude will be going with the first power of this. That is, it will go like the square root of the ratio of the fluctuating potential to the steady state potential. So then, as a first approximation, we can treat these modes as being free modes, not affected by the vertical fluctuating potential. Now, there is a bit of mathematics, but it's important. Let me see how you describe them theoretically. The density fluctuation of the first mode is given by an amplitude, which is dependent on z square. It is the same peaked feature like the plasma disk. It propagates in the vertical direction, but also it propagates in the toroidal direction. This is why they are helical modes. And you see they're rotating with the same frequency as the orbiting frequency. Now the other mode has a similar amplitude in the z direction for the density. It propagates in the same direction, but it is m0 equal to 2. So that when you multiply and couple to them, what comes out is a mode which has no oscillation in the z direction, and it has a frequency equal to twice the orbiting frequency. And this is a perfect coupling with the oscillatory potential. Let me see, how do you find the basic equation? Well, this basic equation is published in an article coming out in a paper to be published by the Russian Academy of Science. Basically, you combine the mass conservation equation in the vertical direction, and you can argue, if you write the momentum conservation in the phi direction, that depends mostly on the vertical velocity, with the momentum balance in the z direction, and you get this rather equation that people tend to identify with the telegraph equation, but in reality it's more complicated than that. And you see, it's second order in the time. It is z dependence, and you can see the definition. This depends on the density fluctuation as well as on temperature fluctuation. This TEI, it is the sum of the fluctuation of the temperature of the electron as well as the nuclei. Why do I include the nuclei? Because the electron thermal conductivity is likely to be very high, so it's very difficult to fluctuate the electron temperature. But it is far easier to fluctuate the temperature of the nuclei. Now, if you, here there is some algebra. Now, we consider temperature fluctuation that, unlike the density fluctuation, they've constant in amplitude. And in fact, we find that they are constant in amplitude, and the electric potential that gives rise to electric field is also constant in amplitude. So that we can argue that this wave will propagate as long as there are charged particles much beyond the disk. And this is why they could be a seed for beams. Now, let's say to lowest order, you take the simplest wave, we may call it an ion sound mode, and then you get a resonance between the basic frequency of these plasma modes and the multiple of the orbiting frequency. Then, of course, you have to go through a series of expansion to find the entire solution that indeed you find. You find that the fluctuation density, they are not exactly like that of the vertical profile, like that of the disk. They are somewhat modified. But this, let's say, is a mathematical detail. And as I said before, the important thing is that this wave will propagate where the density of charged particle is quite small. Now, if you consider, for simplicity of, let's say, presentation, I consider the case where the basic mode is no temperature fluctuation. And the simplest case, again, is that of considering the coupled mode, that must have temperature fluctuation. And in the first case, for simplicity, if it has to have the same mode number in the vertical direction, has to be related to the density fluctuation by this equation. Then when you introduce the mode number, you can see that if the mode number becomes large, this temperature, this is what we want, becomes small. Now, in the case where you allow the temperature fluctuation of the nuclei, which is more probable, then you find that the Ti is the sum of the electron temperature fluctuation and the nuclei fluctuation for the two modes that to differ by this quantity. So this is why I said that if you go with the high mode number, this fluctuating temperature becomes almost equal, and they don't influence too much the structure of the mode. So then, if you have the patience and you study the associated fields, you find that the field is mostly given by the something that looks like an electrostatic potential, but there is a small magnetic field associated with it that corresponds to that of a fluctuating current in the phi direction. So you generate a sequence of poloidal fields. So you have ring currents in the vertical direction. Now, here, then you have to go, and I'm not going to do this here, then you have to couple these two modes. They are pairs. The pairing is not simple like in the case of ordinary wave or plasma wave because they have a structure. So we have done that, and magically it works. What you find is that basically that the coupling of these modes can be comparable to the forcing force of the non-periodic gravitational potential. So this mode can be sustained by the oscillatory potential. It is not the only way to do it. If you have a high energy particle population, then you, by mode particle interaction, you can sustain these modes. But the gravitational sustainment factor is very powerful. Now, I don't know if it is legitimate to consider that around black holes, single black holes, that there are separate planets that modulate the gravitational potential. In that case, you can use the same theory. Of course, you have to take into account the masses of difference, but the driving factor is there. So I'm a bit excited because I think this is a piece of theory that can explain the ejection of waves and then of particles also from a disk of black holes. I think we stop here. Now my time is finished.
Thank you very much for a very nice presentation. And also we have time for a couple of questions. Any question, please? If at the moment probably people are thinking about possible questions, I would like to ask you one question. In your consideration, you mentioned that in your consideration you have very little, very small magnetic field.
Right.
But in many, just one second, I will finish my question. But in astronomers, observers are saying that there are signatures of, let us say, strong synchrotron emission from many sources.
Yes.
Could you comment about this issue?
No, this is fine. You're absolutely right. What I said is this magnetic field is the one associated with these modes. Okay, but now this is something I treated in previous papers. If you consider now the plasma that you can put around a gravitational potential, which is steady state, you create rings, a series of rings of current. You don't get a simple disk, as I described. And these rings of current create strong vertical field. And so if you remember my seminar I gave in Moscow, I begin to study the collective mode that can be created when you have a strong vertical field. But that vertical field is due to other currents that say they're kind of steady state relative to these helical waves. So it is something which I forgot to say, and thank you for bringing that up. Let me, this small magnetic field is only the one associated with these helical waves. Okay.
Okay, thank you.
Then you have to do the theory by including the fact that there can be, and there will be, because simulation have proven that there is a series of rings toroidally that with opposite current that give rise to a vertical field, which is very strong, which we consider to be the one that you see through the synchrotron emission. So your question, thank you. I had forgotten about that point. It's a very important one.
Oh, it was a pleasure. And also interesting thing, when I'm thinking about analogies, I mean, plasma physics and also, let us say, accretion, let us say, flows, streams. But very often when astronomers showed, let us say, accretion structure, it may be not only flat accretion disk, it may be some torus. It's like configuration like tokamak, but
yes,
structure of magnetic field is completely unknown for astronomy, you know,
yeah.
in contrast to tokamak.
Yes, let me explain that. You're absolutely right. So the first thing I did, I wish I had published at the time at Princeton, was to consider like that one, that you can get the same type of equilibrium, similar. And then after going to MIT, I published the first equation of that type, which is called the pulsar equation, we published first by considering an axisymmetric pulsar.
Okay.
Okay, and you're right. They are the same equation that you use for tokamaks. Now, those magnetic fields are very important, and they give rise to other waves. In fact, this is how I met you. I spoke about them when I came to Moscow, but I had not found these helical waves in those days. So then there is an extra magnetic field, which is produced by the currents associated with the steady state potential, in addition to this. And in fact, I postulated something that other people did, that perhaps jets are made by the expulsion of these toroids. You know, they are toroids when they come close to the axis. But there is the problem of keeping them aligned. And we don't know how to answer that question. Now, with this helical wave, you may find a way to keep them aligned because the wave stays aligned. But what you said about the vertical field, which is steady state relative to this fluctuation, is important.
Okay, thank you very much, Professor Copy. It was really a very nice talk and a very interesting reminder. Thank you very much.
Thank you.
Again. So please stop sharing your screen because we have to follow to another talk.
Just a second. Thank you.
Okay, thank you very much.
Thank you.
Odele, do you hear me? Odele.
I do. Hello, I'm
yes.
here.
Hello.
I will share my screen now.
Yes, please do it. Okay, good. Okay, go ahead. 35 minutes for talk, and it's sorry, but I forgot to introduce. It's according to to my opinion, so it's one of the most important and beautiful experiment. It's a interferometer in optical and infrared band. So it's excellent. And also in last years, they got excellent result about predictions of general relativity for the galactic center. It's very important because in last period, people suggested some alternative models where so general relativity is not valid in some objects, just to explain dark matter, dark energy problems, but also we have to prove in an experimental observational way that is general relativity is fundamental law of nature. It was confirmed in this experiment and observation. Thank you.
Thank you very much for this really nice introduction.
Thank you.
And a big thank you also to the organizers for having me speak here. It's a real pleasure to be part of this beautiful conference. So gravity, infrared interferometry, and how to test general relativity in the galactic center. So my name is Odel Straub and I'm from the Max Planck Institute for Extraterrestrial Physics in Garching, and I'm talking to you on behalf actually of the Gravity Collaboration. We are about 50 people from 7 different institutes. So we have the MPE where I am from, there is the Lesia in Paris, there is BH1 in Cologne, we have SIM in Lisbon, there is another Max Planck Institute in Heidelberg, the IPAC in Grenoble, and of course the ESO, which has the European Southern Observatory, which has its headquarters in Garching, and of course the telescopes in Chile in the Atacama Desert. So first things first, I would like to start with a little bit of theory. And when thinking about theory in the context of general relativity, one immediately has also to think, of course, of Marcel Grossman. Einstein wrote to him a little note in 1912 saying, "Grossman, you have to help me or I'll go crazy." And he wrote that when he was deep in trying to convert the special theory of relativity to the general theory of relativity, and he was missing the mathematical tools to describe the curvature of space-time. And Marcel Grossman was actually the one who introduced him to things like Riemannian manifolds, Ricci tensors, Levi-Civita connections, and basically the whole toolbox needed to come to general relativity. And I'm just writing down here at the bottom right, Einstein's field equation, even without gravitational cosmological constant, just to show you that you can separate nicely the geometry part from the matter part. But even if you consider a vacuum, the mass, the central mass, the gravitating mass, it is intrinsically connected to the space-time. And John Wheeler has this really beautiful quote which says, "Mass tells space how to move, and space tells matter how to curve, sorry, and space tells matter how to move." And we are now talking not anymore about the Newtonian instantaneous force, but about a field that propagates at the speed of light and that curves the environment. And this comes with all kinds of interesting effects. Carl Schwarzschild in 1916, soon after the publication, solved Einstein's field equation for this gravitating mass without any matter around it, so g mu nu equals 0, and the result was the Schwarzschild metric. And I wrote down here the line element for you just because it's beautiful. And if you now, so this is considered now the classical gravity, and if you want to go from here to a generalized theory of gravity, maybe a cosmological theory, what you have to do is you have to take the generalized Einstein-Hilbert action and you can modify it according to your needs. You can add a cosmological constant, or you can add scalar fields or functions, for example, f of r, where you have another Ricci scalar involved. And this will end in non-vacuum solutions or potentially Lorentz violating solutions. What one has to pay attention, of course, is that the action principle is valid. So you solve the delta S equals 0 and you get your theory of gravity from it. And this now can be tested. So whichever theory you come up with, it has to be tested against observations, naturally. And this has already started during Einstein's lifetime with the 3 classical tests of general relativity. On the left, I just show you Earth and the moon immersed in a curved space-time, symbolically, of course, because this has been tested on Earth and in the solar system. So there is the test of gravitational redshift, which has actually been tested by Paun and Repka at the Harvard-Smithsonian Center for Astrophysics, where they were using the Mössbauer effect, basically just shooting a laser from the bottom floor to the 3rd story of the building and checking how the light is affected by the gravitational field of Earth. And there is the second test is the precession of Mercury, which has been done even before the gravitational redshift, which is about the fact that Mercury, the planet, it is not orbiting the sun on an ellipse, on an elliptical orbit, but it is orbiting on an open ellipse, which has to do on the one hand with the Newtonian effects from all the other planets, in particular Jupiter and Saturn, but there is this extra kick due to general relativity, which Mercury gets every time it passes at the perihelion close to the sun, and this has been proven to be exactly how Einstein predicted it. And then there is the deflection of light, which I show on the bottom right. That's actually a photograph from 1919, the solar eclipse in 1919, when Eddington was measuring the deflection of light. So there were stars suddenly visible, which have not been visible before because their light was traveling in the curved space-time on a bent trajectory. So there are now actually various tests of general relativity, tests which one can do with gravity theories. And this is a collection of all of them, or kind of the different types. What is shown on the x-axis here is the log of the mass in grams, actually. So if you know, Earth has 10 to the 27 grams. So the bottom point here shows, well, on the y-axis is the gravitational, the strength of the gravitational potential. So the first point here is the Paun-Repka experiment on Earth. The precession of Mercury is over here, now with 10 to the 33 grams, that's the sun. Here we have all kinds of solar mass types of objects. So also white dwarfs, pulsars, the Hulse-Taylor pulsar. The gravitational redshift has been measured with the binary with Sirius B. And when we're now thinking about the gravitational strength of our own object in the Milky Way, we are up here in this range. And I will talk about this in the following. We have the S2 star, we have S star orbits around the compact object in the galactic center. And this allows us to probe actually a rather large range of the potential. And then, of course, there are AGNs and where one can measure the iron line. There are massive black hole mergers and potentially then supermassive black hole mergers, which can be measured with LISA in the future. Next to the classical tests, the 3 I mentioned before, there is also the Einstein equivalence principle, which is one of the test beds, so to say, for any theory of gravity. And the road to go is basically what we want to do now is we want to get the best data possible. We want to test GR, and then we want to test alternative theories of gravity. So first things first, let's start now in the Milky Way. Here on the left, I show you a picture from the ESO. This is one of the unit telescopes in Chile on Earth. And this is actually Unit Telescope 4, which has a laser. With this laser, it creates in the atmosphere an artificial star, so-called a guide star. And it points in this picture, it points directly into the galactic center. So this is why I show it here, the galactic center, here in the Milky Way. Right where it is at the same time the darkest and the brightest. The challenge now is to observe anything in the galactic center, our place in the Milky Way. We are here where it says in German, unfortunately, it's the sun. The sun is here in the kind of the outer half of the Milky Way. And if we want to observe the stars in the center, we have to peer through all the stardust and through all the molecular clouds. And this cannot be done in the optical. There is a large amount of extinction. So we have to be creative a little bit. And I'm showing you here a zoom in from Earth, basically into the galactic center. And it starts out with optical light. And you see you have these dark, obscuring clouds. And if you want to see more, you have to actually change the wavelength. And we're changing now. Now that you start to see the orange glow, we're changing to infrared. And what opens up to our sight is basically, I mean, it's a myriad of stars. The galactic center is an extremely busy place. There is a compact nuclear star cluster in the center, which contains bluish, here you see them in the center, bluish young stars. And if we zoom in even further and further and observe these young stars and check what they're doing, we see that they are moving, and they're not moving just in any old sort of way. They're actually moving around a common center. And now to clarify this a little bit more, we put the stars we observed into the computer and put orbits on them. And what you see here very beautifully is that they are orbiting a common center of gravity, a dark mass. And the quest now is to find out what kind of a mass is this, what is the size of this mass, and does the theory of gravity we know, does it hold, and what about other theories of gravities? So here, in summary, again, the scenario we have in the galactic center. On the left, you see again this really dense star cluster with some prominent stars. So there is a star called IRS-16c, which we are using for phase referencing. I will come to that in a minute. There is the star S2, which is on a 16-year orbit around the galactic center compact object, which is called Sagittarius star, Sagittarius A star. So this is one of the things we can consider. And the other things we are interested in is the variability of the source Sagittarius star. And this is shown on the right-hand side here. The source is extremely variable, basically in all wavelengths, and in particular in the infrared and in X-ray. So this gives us also some clues of what is happening in the galactic center. And I will show you in a minute what this is all about. So we have the S star cluster, which is really close to the black hole. It has semi-major axis between about 100 and 800 milli-arc seconds. And then, of course, Sagittarius A star with an apparent diameter of 53 micro-arc seconds for a zero-spin black hole. And what we now want to do, if we want to observe this, we want to have a sufficiently high resolution to follow the stars on their orbits. So in the case of the star S2, which has an elliptical orbit here sketched in red, if we think of an analog on the moon, this would have the size of a football stadium on the moon. So the whole orbit would, resolving the whole orbit would correspond to a football stadium on the moon. And to follow the star on a tens of micro-arc second resolution level, that would correspond to resolving a €1 coin on the moon. So if we plug this into this equation about the angular resolution, we get out a diameter of a telescope of 100 meters. So that's what we would have to have in order to make such observations at a wavelength of 2.2 microns. Now, a 100 diameter telescope is fairly tricky to get. I mean, it's technology, it's not really possible to make such a large dish. But what we can do is actually we can apply a trick and we can create ourselves a virtual telescope. So this brings us to Gravity, now in capital letters. Gravity, the instrument. On the left, you see the VLT, the Very Large Telescope in Chile, which has 4 8-meter telescopes called the unit telescopes, and they have different baselines among themselves. So you can create 6 different baselines among these 4 telescopes, and the longest baseline of them has around 130 meters. So this corresponds, if you connect all these telescopes, this corresponds to a virtual telescope with a diameter of 130 meters, and this is precisely what we need. So we are connecting all these 4 telescopes, and we are creating an interferometer out of it. And Gravity, in fact, is an instrument called, it's a beam combiner. It combines the 4 beams of all these telescopes. So that's how it looks, actually. This is underneath this telescope platform. It's guiding the light from each of the telescopes with optical fibers and mirrors, and it's combined, and the signal is interfered. I will show you later a bit also how this works. There are 2 very important technologies involved in order to meet this requirement of very high resolution and very high contrast. On the one hand, this is the fringe tracking concept. This means we are pointing at the galactic center, here marked as GC, but at the same time, with a second fiber, we're also pointing at a phase referencing star, which allows us to stabilize the fringes of the instrument. And in effect, this allows us to integrate longer on faint objects. And the second extremely important technology is adaptive optics. So this uses a guide star, which I mentioned before. In our case, it uses an actual star, IRS-7, and this is used to correct the atmospheric turbulences between us and the galactic center. So this is a correction that happens in real time with a deformable mirror, and you can sharpen like that. You can sharpen the images considerably. And here is the scheme, the schematics, how this actually works. On the left-hand side, we have here 2 telescopes, and we have the wavefront, which comes from a distant star. It hits one of the telescopes first, and then the second one. This delay is corrected underground with small cards, which are correcting this. And it's that the light beams are guided through a series of mirrors into the instrument where they are interfered, and they are creating this interference pattern. And from this, we get basically 2 physical quantities. One of them is the phase, and the other of them is the visibility. And the visibility is, in essence, the fringe contrast. And this allows us to get the positions of an object and its size. So now we're going to look what happens, what can we get? We're going now back from the sky to the paper. And these are the results we have received since 2018 and published in a series of papers. We have been tracking the S2 star orbit. Here you see it in black, and we have in blue marked the gravity data, the new data. Gravity allows us to be 1,000 times more, it's 1,000 times more precise actually than previous instruments. The other data here are just by a single telescope, the single 8-meter dish telescopes. We can split the orbit into right ascension, motion over time, and declination over time. And we also measure with a spectroscopic measurement the radial velocity here, marked. The instrument is called Symphony, and we also have some Keck data, some public ones. And from these data, from these positions, we get over the night and over the months and over the years, what we basically do is we are fitting, well, the idea is to use the third Kepler law in essence, and to fit an orbit, an ellipse to the data. But of course, we're not using Kepler, we are using Einstein's full general relativity. But in essence, this is how it works. you need to know the semi-major axis, you need to know the period, the time it takes for the star to orbit the black hole, and you can fit for the free parameters, and we get out of this the mass of the central black hole, 4.2 times 10 to the 6 solar masses, and the distance to the galactic center, 8.2 kiloparsecs approximately, and the specifics actually of the S2 orbit, semi-major axis, eccentricity, and the period. And also, if we use full general relativity, we get out of it that the orbit is precessing, and it changes by 12.1 arc minutes per orbit. So this is the angle it precesses at the pericenter of the black hole. And so our main results over the past 3 years were actually the S2 redshift and the S2 precession. And the way we get this is we are basically subtracting a Keplerian orbit from the fully general relativistic orbit, and we get out an excess of around 200 kilometers per second. Here, these spikes at each pericenter passage. If we were only to consider Keplerian ellipse, there would be no such excess, but these 200 kilometers are in fact due to the gravitational redshift, if we take this into account, and the data match this perfectly. And similarly with the Schwarzschild precession, so we are subtracting the two different orbits, Keplerian from the general relativistic orbit, and we see that there should be, in right ascension, there should be some deviation due to the rotation of the whole orbit, like with the precession of Mercury, so the precession of the S2 star. So there is a deviation expected, and the data follow precisely this predicted Schwarzschild precession. What we also can do is we can test the equivalence principle, or at least a part of it, namely the local position invariance, which says that you can, if you do if you do an experiment which is a non-gravitational experiment, and you do it in different strengths of the potential, the outcome should be precisely the same. So we are looking now at atomic processes in the star S2. So we have a helium line and a bracket gamma line. And we are measuring these two lines spectroscopically, once when S2 is far from the black hole and once when it is near the pericenter of the black hole. And you subtract the two, and what you get out is something that is extremely close to zero, which means that the local position invariance holds indeed in this case. Now, this has been tested to much higher precision in Earth laboratories and other experiments. So the experiment with the S2 star and Sergey star, the supermassive black hole or supermassive compact object, this is not the most precise of all tests, but it involves the largest shift in gravitational potential. So this is nonetheless a very important result, actually. Now I'm coming to a little bit of what happened recently in the galactic center. So we have been following the star S2 on its orbit around around Sergey star. And what you see here on the black line is, so we have on the x-axis we have time, and on the y-axis there is the three-dimensional distance of the star from the black hole. And you see here S2, it approaches the black hole to a distance of around 14 milliarc seconds, and then it goes away again. And now it's already at, I don't know, around 130 milliarc seconds away. So it's already going far out now. And we realized early this year that there are actually a bunch of other stars approaching the galactic center. And notably one, the blue one here called S29. So that's another of the S stars, and it is also like S2 on a very eccentric orbit. The eccentricity is more than 0.9. It is, however, on a 90-year orbit. So this is, one has to be patient with that one. However, this year it approached its pericenter just a few months ago in May, and its closest distance to the black hole is only 12 milliarc seconds. So that's closer actually than the S2 star. And then there are some other stars which are slightly further away, but also have their pericenter passages in the near future. And this is, of course, very interesting for us, and we are tracking them as well. And the way we're doing this is by something which we call the multiple targeting. So during a night, we are calculating the predictions where we expect the stars to be. So we have the orbits which we think which we received from previous data. We mark here with the grubby little stars the expected position. In this case, it was for March this year. And then we are pointing our telescopes, the fibers, directly at this position where we expect them. And what you see here, what is interesting in the galactic center, very close in, if we point at Sagittarius star, which is marked by the yellow star, we always also see S29 in the same field of view. The field of view is now is marked here as this gray shaded area. So we see it at all times, and this is extremely useful because now we can track the separation of S29 and check whether it's actually following the orbit we thought it should follow. And indeed it does. So here I show you, well, 3 different orbits. One of them is the S2, our known orbit. And what I would like to point out here is the zoom in. So the zoom in shows all the data of this year. We have had the chance to observe 1 week in 3 different months. So we have in March, we have the data set here, in May here, and in June over here. And they are following almost exactly the predicted S2 orbit. So these are these very tiny, tiny stars. And what you also see is the previous measurement, which is following nearly perfectly, well, that's of course from the FIT, the previous orbit here. So these are NACO data. So with just one telescope, and the small stars here are the gravity data, and you can really distinguish now that the pericenter has advanced and that the orbit is moving in a prograde fashion. So this is actually a very beautiful outcome. And what you also see is this new star, which is coming in close to the black hole, which is S29. And again, we have these 3 different epochs where we observed March, and it travels towards the black hole here in May at the bottom. And in June, it's already starting, it's kind of around the corner and starts moving out. What we also see is something really interesting. We see an extremely faint star. We don't know its orbit yet. It seems to move on basically just a straight line, but we don't have so many data points yet. But we can see this really faint star of a magnitude of almost, of a K magnitude of almost 19. We can see this as well in our data. And I'm not quite sure why there is an umlaut on the approaching, but yeah, don't mind that. What I would like to show you now is we can actually, well, with gravity, we can also make images of our stars, not just get the position and the rest. So I made with the Myra software, I made a little movie out of this image reconstruction. And what you see here is, again, the star S29 imaged now, and we can see how it moves on this orbit from March to May to June. And so this little movie has now been tuned so that we can very well see S29 and the black hole, which you see here, which becomes brighter and fainter, by the way. But we can also go deeper and then extract the position of S62, this really, really faint star. So I mentioned this variability of Sagittarius star, and this is just a snapshot which I really like, which has been taken in the control room by Thomas Ott in 2019. And this is just made with the cell phone, with the mobile phone. We were pointing at a collection of frames we took, a collection of exposures we took during the night. And what you see here is there is a flickering just above the mouse, and it becomes as bright as the star next to it. And you can guess from the excitement that this is actually Sergey star, the variability of Sergey star over an hour, and it becomes nearly as bright as the star S2. So Sergey star is variable in the infrared. It is also variable in X-ray. It's basically over the whole band. This is with different instruments, is a record of this variability. And the interesting thing about this variability is that it occurs typically once per day, and it occurs for around 30 to 60 minutes. So when we're able or lucky enough to catch it, to capture it, so there is a flare, kind of a small burst between 30 and 60 minutes. And this is, of course, very interesting because this time scale, this corresponds to the ISCO. So we are probably talking now about the strong gravity regime. So we need to have a closer look at this flaring variability. And in 2018, we had the 3 beautiful flares. And what we noticed is there is a motion on the scale of around 150 micro arc seconds. And this motion appears to go in a clockwise manner. And on the left, you see our most beautiful flare, which we could trace over the period of around, I think this one was around 40 minutes. The light coming from Sergey star, it moved on a scale of around 150 micro arc seconds. There are other flares which behave quite similarly, but it's not that they are fainter and it's more difficult to see the circular motion. But there were others. So on 28th of July and 27th of May in 2018, we noticed a similar clockwise motion of the light coming from Sergey star. The flux can have 2 different shapes, basically. It can come as a double peak, or it can come as a single peak. And the difference between the ground, kind of the quiescent state, and this kind of flaring up, the difference is not very pronounced, which tells us that we are probably looking at more or less, well, not face on, but at a low inclination. If the inclination would be higher, there would be a stronger difference in flux. So we are looking at something that, if it's on a circular orbit around a compact object, it is some kind of at a modest inclination. We can also measure with gravity the polarization states, actually. And what is shown here on the left in blue is again this double peaked flux. So there is the flux variation during one flare. And what you can see here in red and green is that the polarization, basically in Q and U, it varies on the same time scale in a sinusoidal way. So there is a circular motion also connected from the polarization state, and you can plot this as Q versus U, and what you see is that it follows also this kind of clockwise motion. And the important thing is, which we noticed, is that it is just one loop. And this tells us something about the nature of the magnetic field that is present. If we were talking about a purely toroidal field, we wouldn't record 2 loops, in fact. But since we only record 1 loop, we know that there is only one revolution. It means that we are most likely talking about a mostly poloidal field. There maybe is a toroidal component in it, which is still allowed by the observations, but it's probably mostly a poloidal magnetic field, and it's an ordered magnetic field. So that's what we can say from the polarization measurements. Now I would like to just shortly mention there has been recently talk about a very interesting alternative. Namely that in the galactic center, we maybe do not have a black hole, although, I mean, all our results, as you saw, they are completely conform with the general relativity of general theory of relativity. But suppose we are replacing now the center of the galaxy, of the Milky Way, with a dense core. So the model that has been proposed recently is, well, it's actually not a very recent model, but it has been in the news recently, that we have a dense core of dark matter made out of 65 keV fermions. And the authors, Becerra Vergara and collaborators, they found that the orbits in this potential, they fit perfectly. What you see here is the gravitational redshift, which they beautifully get out. It matches the data. The S2 orbits can be fit very well in this potential as well. So it seems that the dense dark matter core actually passed a number of tests already. However, it didn't pass yet all of the tests. The problem is that the size of such a dark matter core is actually too big. Such a dark matter core, in particular one with 56 keV, it would have a size of 0.4 milliparsecs or 10 milliarc seconds. And that is larger than the size we see from the flares. The flares, as I mentioned, they are on the level of 150 microarc seconds. You can make this dark matter core denser, but you cannot make it dense enough to match the observations. Here, the radius of the size is on the x-axis, and the period of the variability is on the y-axis. So the red points here are our flares. The orange line is another measurement entirely, namely a radio, so a VLBI measurement at 1.3 millimeters, which measures a size of 37 microarc seconds, which is probably some kind of a beamed emission from the resident accretion flow. So these small sizes are not matched by this dark matter gravity, unfortunately, but it's a very interesting theory for other intents and purposes. Now, just as a quick outlook, if we want to measure the spin, we could, of course, use or consider using the flares, perhaps with an upgraded instrument, Gravity Plus, but flares are really messy. They contain accretion physics, B fields and everything. A cleaner way would be to have actually a star on a smaller orbit, a star inside the S2 orbit. And so this is what we are looking for now. We want a star on a very small orbit. And here on the right, you see what kind of an orbit and what kind of an eccentricity you would have to have if you want to measure the black hole spin. So the message is that you would have to have a star that is on an orbit around 10 times smaller than the S2 orbit and at an eccentricity as high as possible, basically. And this is just the summary of what I told you today, that with gravity, the instrument, we have been able to test GR. We have extracted the gravitational redshift. We could test the local position variance. We measured the Schwarzschild precession. We detected really faint K magnitude 19 stars, and we see this orbital motion of a flare near the black hole. And if there is another gravity theory, these are the things that one has to consider and which has to match the theory of gravity. And that's the end. Thank you very much. You are muted. I think you're talking, but you're muted.
Okay, I wonder. We don't hear you.
Yeah, Alexander, you're muted.
Oh, okay, sorry. I
Yeah.
recommended Professor to unmute yourself, but I forgot to unmute because I was so impressed. So it's it's excellent talk, but it's also my remarks later, because it's, and also orderly should check my remarks. Professor, please, your question.
Okay, well, it's
Professor Copy.
talk. I agree with you. Now, you touched on variety of subjects. Now, when you say that the magnetic field is poloidal, you're referring to stars where there are no flares. Could you expand your idea of what the origin of the flares are?
So yeah, so I was referring to just the flare motion which goes which has been observed around Sergey star. We do not know precisely where these flares come from. What we know is that they have to be, I mean, the electrons have to be accelerated considerably. And what we think currently what happens is that there is magnetic reconnection events that accelerates and heats up the electrons in some kind of in a bowl, in a plasma bowl, which then circles the black hole and is being accreted. What we cannot say from our observations so far is whether this happens in a plane or whether this is being lifted above the plane. So we cannot distinguish right now whether this is just a purely circular motion or whether this is perhaps something connected with the launching of a jet or a failed launching of a jet or something. We think currently that the whole flare mechanism, it matches rather well the accretion disk scenario called MAD, which is the magnetically arrested disk scenario, where strong magnetic fields are channeling basically the matter, the resident gas, and heating up by magnetic reconnection things. But yeah, there is no way right now to tell.
Okay, other questions? If not, I would like to say something. But Odile is a leading expert in this field. You have to correct if something will be wrong. So first, you mentioned that black hole size for Sagittarius A 53 microarc second. It seems to me that you meant shadow size you said for Schwarzschild, but it's in some sense shadow size does not depend on spin. It's, I mean, shape of shadow depends on spin. So, but size is almost the same for all values of spin. And second, remark about it's correct. Yes, probably you agree.
No, the black hole size changes with spin actually. So what I mean is the apparent size of the horizon so the apparent horizon is.
Okay. But the
apparent horizon so in theory, the apparent horizon has a size of 10 microarc seconds, but it is lensed gravitationally by a factor of square root of 3 times square root of 3. So this gives you an apparent size of 53 microarc seconds, and this is for a non-rotating, and then the horizon will shrink and become deformed as you add spin.
Yes, but in vertical direction, size is the same. It's a theorem. It's we also proved theorem so about this. In vertical direction is the same, but it's no matter. Just also some, let us say, since you mentioned Grossman-Einstein, you started since Grossman-Einstein. So, and also when people, sometimes amateur people asking, Schwarzschild found solution of Einstein equation only less than 1 year after Einstein formulation of the equations, but he found solution for vacuum. In principle, these equations were known for years before final version of Einstein, just for people who are interested in let us say, this subject. And second issue, probably you have to correct my point because probably I'm wrong about adaptive optics. So adaptive optics based on Kolmogorov model for turbulence. So, and sometimes people are discussing, so mathematicians are completely useless for technology and other things. So, but practically this insight about turbulence behavior was very useful, and practically it was realized in technology. Is it correct? So
yes, yeah. And there is actually, so there is this wavefront sensor, which is measuring this, and then it's correcting,
yes,
basically working like a noise cancelling headphone, but it's kind of a turbulence cancelling motion.
And also about precession and extended mass distribution. Practically, you said that this was confirmed. I mean, Einstein prediction about precession for S2 star, but in this case, you could derive some constraint for extended mass distribution, let us say for dark matter or stellar cluster,
Yes.
etc., inside this orbit. How much this constraint, because you have to derive limit on extended mass distribution as well.
So the extended mass, it can be different things. It can be a sea of stellar black holes around the other S stars, but it can also be a concentration of dark stuff inside the S2 orbit. And given our measurements, the allowed extended mass is less than 0.1 times the mass of such a star. 0.1% of the mass of such a star.
Okay, great. Thank you very much. Yeah. Also, last question about polarization of blobs and other things. So, in principle, it seems to me that in your paper you wrote that is origin of this polarization is synchrotron emission. In this case, probably you have an opportunity to evaluate magnetic field somehow for near these blobs, or not?
Yes, that's what we try to do, and so we saw that we have a linear polarization, and that and we can give it to some certain confidence. We can give it an orientation. We think that also in the non-flaring state, so there is polarization present, but this is still ongoing work.
Okay, thank you very much. If there are other questions, Stanislav, do you want to ask question? Last question. Please,
yes.
Short answer.
My question is about the data of gravity calibration, and I am working in the field of theoretical investigations of redshift of stars in general theory of relativity, and I am interested in raw redshift data for stars that have very short orbits around the supermassive black hole. And if it is possible, maybe you can recommend the address where I can find such data if they're open.
So the gravity data, a lot of them are now publicly available in the ESO archive. ESO has a raw data archive. And otherwise, I propose you write to one of us, to one of the gravity collaboration members, and we can see whether we can collaborate on something. But so the data are becoming publicly available. Not the ones from this year are not yet available. It takes a year to become publicly available.
Yes, I can just write for you, for example.
I think this would be the easiest, yes, and also in order to let other speakers continue today. So yeah,
thank you very much.
Yeah.
Thank you very much again for your impressive, excellent talk and also description of these observations, and also good luck for future observations from these ELT. I hope you will have access to these facilities. Thank you very much.
Thank you. Would be a whole other talk about that, yeah.
Yes, thank you. Thank you. Thank you, bye. And the next speaker is, it seems to me that is Eva Hackman, yes?
Hi, everybody.
Yes, hi. Please share your screen. You have 17 minutes for talk and 3 minutes for questions and discussion. Please go ahead.
I will try to be on time. Thank you.
Thank you.
Okay. Just a moment. I try to go full screen. Yes. Okay. So I will talk today about near horizon particle collisions, and particularly in spherically symmetric spacetimes. And this is work in collaboration with Nandan, Chioran, Lukamendi, and Abebe. And so this is the plan of my talk. I will first give you a short introduction on what this actually is I'm looking on and why this is interesting, and introduce to you or remind you of what is sometimes called the Barnard-Silk-West effect, BSW effect. And then I will present to you the generalization of this effect, including spinning particles, and consider a particular example or setup of this type of collisions very close to the horizon. And lastly, I will summarize. Okay, so, well, the topic is particle collisions, and they should actually be very common close to black holes, because we have a lot of things going around black holes, particularly supermassive black holes. So we have accretion disks, we have clouds and stars going around, or other maybe elementary particles, radiation, and so on. And the question is, can such particle collisions maybe provide some unique signature of a strong gravity, so close to the black hole? And there was a seminal paper by Barnard-Silk and West from 2009, and I will refer to this as a BSW paper. And they discussed two particles, so actually a rather simple setup. So they had two particles coming from infinity, at rest from infinity. They should collide somewhere close to the horizon of a Kerr black hole, and they computed what is the maximal center of mass energy at the point of this collision. And what they found was, amazingly, that if you consider the very special case of that you have an extremal Kerr space-time, so rotation or spin is equal to mass, and that you have a fine-tuned angular momentum of the two particles, then the center of mass energy can grow without bound. It can become infinitely large if you shift the point of collision to the horizon. So this is actually rather amazing. So why should this happen, or why does this happen? And immediately after this paper appeared in 2009, there were two other papers by Berti et al. And Jacobson et al. And they discussed if this scenario is actually realizable, or say likely to happen near to an astrophysical black hole. And they found actually, no, this is not very likely to happen, because of a number of reasons. I will not, due to time, I will not go into the details here. But the question arises, so if we go to some other space-time or to some other gravity theory, if we consider some other particles or setup, can we maybe remove some of the obstacles that prevent this scenario to be likely close to a supermassive black hole or astrophysical black hole? So let me go a little bit more into detail here for this BSW effect. So they assumed that there's a Kerr matrix. So we have two killing vectors giving us a constant energy and a constant angular momentum for geodesic particles. They restricted to the equatorial plane to make things easy. They assumed that the particles start from rest at infinity. So this sets the two energy parameters of the particles. And they assumed that they collide at some point RC close to the horizon. And then they computed the energy in the center of mass frame, and the formula is given here. You can rewrite this a little bit to get this expression here. So here are the two form momenta of the particle and the masses. So now you can use your constants of motion, and for simplicity, you can set the two masses to be equal, but you can also do this with different mass. It does not matter very much. And then you can compute the center of mass energy again, and you find this very nice formula here. And if you now take a look at that, you see that, okay, potentially it should diverge, of course, at the singularity. So at the singularity, the rho is 0, but this is not so much interesting. But here, it actually looks like it could also diverge at the horizon, where this function delta here is equal to 0. So, but actually in general is that it does not diverge at the horizon, because this P here, P functions here given below, also get 0 at the horizon. So if you do the limit, then you find this expression here, where RH should be the horizon, the outer horizon. And then you actually see, okay, in general, everything should be really nice and finite here. But there is a small loophole here. So now you have these p's here in the denominator. So of course you could say, okay, if one of these p functions here, which is given, involves the radius and the constants of motion, if this is 0, of course, then this could diverge. So this is like the idea, basic idea of Banach, Silk, and West. And now you can, of course, choose your angular momentum such that this p becomes 0, but then you see that actually the geodesic particle cannot reach the horizon, because here you see the radial component of the force velocity. It looks like this here, and you see if a particle, a geodesic, comes, it will have a turning point here and go back, so it cannot reach the horizon. Here you see this for a spin of 0.9. If you now increase the spin, you see that this barrier here, potential barrier here, decreases and you can come closer to the horizon. And if you actually go to the extremal case, then this turning point is exactly at the horizon, and you can realize this infinite center of mass energy that Banach, Silk, and West found in their paper. So you have that this p equal to 0 actually implies that you cannot reach the horizon unless you have an extremal horizon where a is equal to m, or a is equal to 1 in the, or a over 1 is equal, a over m is equal to 1. And if you have this particular case, then you need a specific value of your angular momentum, and this is 2m. So in the following, I want to show you how this picture changes if we do not look at geodesic particles, but if we do look at spinning particles. So we take some of the structure of the particles into account. And then the question is, can we solve or say circumvent this problem that you cannot reach, that there is a potential barrier that like forbids the particle to reach the horizon unless you have an extremal one. Okay, so what is the equations for spinning particles? So we use what is called the Matheson-Papapetrou-Dixon equation. I did not write them down. I think they will not say you very much if you don't know them. They are just involving, say, the spin of the particles. And if the spin gets 0, you get back the usual geodesic equation of motion. The MPD equations, Matheson-Papapetrou-Dixon equations, are not closed in the sense that you need a supplementary condition to get a full system of equations. And the spin supplementary condition, we chose this one here, called the Tolchiev condition. This actually is related to your choice of the observer that associates the reference word line in your worldview with the center of mass. So what you choose here is basically given by convenience of the problem we are looking at. So we restricted to planar motion. This means that the spin of the particle only have a theta component, so that everything remains in the equatorial plane. And we assumed a static and spherically symmetric spacetime, which you can write down in this form here, where you have here some function f of r, and your horizons of the spacetime are at the zeros of this function f of r. We see it here in the denominator. And because it's static and spherically symmetric, you have conserved energy, you have conserved momentum. And in addition, you have, due to this choice of the spin supplementary condition, you have a conserved spin vector for spin s, squared spin vector, and you have a conserved dynamical mass m related to the form momenta of the particles. And then you can have these three, say, constants of motions in your equations. And this is then what you get for the equations of motion. And what is most interesting for us is this one here. So the radial equation of motion, it has a nice form. We have again some kind of P. I wrote it curly here. It's not the exact same thing as the Banach-Silk-West approach, but similar. And then this factor here. And what you should note here, so the structure is very similar, but here in the P and also in the L, you have a denominator, which I abbreviated as capital C here. And this capital C can get 0 for specific choices of the spin of your particle. So it might be that if this is 0, your P and your L diverge. And as you may expect, that may give you some additional points where we can have diverging center of mass energies. So if you again evaluate the center of mass energy, you get this here, this expression here. And you see it is again potentially divergent at the horizons where F is equal to 0. And it is potentially divergent at the places where P and L get infinite. So where this function capital C here gets 0. So let's first look at this second case here, because this is somehow something which is intrinsically connected to the spin. So, but at least for the spacetimes that we checked, so we took a Schwarzschild plus some quintessential matter background. So this gives us an F in this form here, with some particular choices of epsilon and free lambda, parameter lambda. At least for this, you find that the point where the C becomes 0 is always behind the horizon. And the reason for this is the Möller bound. So this means that the spin of the particles cannot get too large compared to the radius of the particle, because then the particle would spin with superluminal speed. So this is somehow forbidden. And because the size of the particle is much smaller than the size of the horizon, you can show that the C equal to 0 is always behind the horizon. Actually, I would conjecture that this is always the case, but we couldn't show that for like a general choice for this F function here. And in addition to that, at this point where C becomes 0, the 4 velocity switches also from sub to superluminal. So this is also some point, some argument why this point is actually not physical to consider in astrophysics. So to conclude this second point here, so this is actually not something that is astrophysically interesting for us. So that remains to look at the point again at collisions at the horizon. If you do the limit, you find this here, this expression. Here, again, you have the p's here in the denominator. It is generally finite, but if these p's here, these expressions become 0 at the horizon, then we could again get this diverging center of mass energy. But we have to check, as we learned from Bernadotte and West, if we can reach the horizon under this condition. And to check this, we rewrote this function f that defines the horizon in this way here. So we explicitly factored out the 0, which is associated to the horizon. Then we solved P, for example, for the energy, giving us this here. And then we expanded our radial equation of motion close to the horizon. And we found actually that this here will always be negative. So there will be a potential barrier that prevents the spinning particles to reach the horizon, at least if you do not have an extremal one. If you have an extremal one, but I will not go into the details, it might be that under special circumstances, you could realize something like this. But then you are exactly at the same point where you were with the Bernadotte and West argument, that probably this is not very likely to happen, actually. Okay, then we thought maybe there is another possibility. So we thought maybe we do not do the collision exactly at the horizon, but maybe only close to it. So we assumed that the collision point, RC, is close, but not exactly at the horizon. So this should be very much smaller than 1. And then we do, we make an assumption on one of the two particles, and we say it should be what we call near critical. So we choose the conserved quantities, energy and angular momentum, such of this particle, such that this function P is positive close to the horizon, so at this collision point RC. And we say it should have this form, where D is some constant, and here we have the square root. And of course, we checked, you can realize that it is possible. And the second particle should just be generic, some particle. Then we again computed the center of mass energy, and what we found was this here. So here now in the denominator, you have this square root expression here, RC minus RH. And if you now come closer and closer to the horizon with this collision point, then the center of mass energy will grow without bound. Okay, so this is very interesting. And what is even more interesting is that we realize that this does actually not depend on the spin of the particle. You can do the very same thing without a spinning particle. So for a geodesic. So in the limit that the spin vanishes, you can do the same thing. This P is then just the energy of the particle. You just choose it in that way. And then you can do the very same calculation, get the very same result. So it is not a specific signature of spinning particles, but some generic thing. Okay, but there is a big but to this. So by construction, that particle, that what we call a near critical particle, can reach the horizon. But in general, this particle then cannot come from infinity. It has to be created somehow close to the horizon. It usually means that this near critical particle should have a very small energy, for example, if you consider the spinless case. So the question is it possible to have such a near critical be created by some process close to the event horizon? So our first thought was maybe this can be done with multiple collisions, and actually Zaslavsky, which I think is the next speaker actually, showed that this is actually impossible for geodesics in Schwarzschild spacetime. So this is not a possibility to realize infinite center of mass energies for geodesics in Schwarzschild. But he showed that if you go to an extreme Reisner-Nordström spacetime, then you could, in principle, do that if you have foregoing collisions of charged particles. But the resulting charged particle will, of course, be neutral, so it will be a geodesic. So this would be a possibility. But again, of course, this is rather fine-tuned, so this is not actually what we were looking for. We did so far not check other spacetime or spinning particles, so it might be that this multiple collision scenario might still be feasible if you go to some more general settings, say. And then another idea that came only lately to us, which is actually natural, I don't know why we did not think before of it, the particle could also be created close to the horizon by, for example, by Hawking radiation or so on. But we did not check into this in more detail until now. Okay, so let me summarize. I told you what actually the BSV or Banach-Silk West effect is. You have a particle collision at the horizon that can, in principle, generate infinite or say Planck scale energies, which would be very nice to test our theory of gravity, of course, or say signatures of quantum gravity or so on. But unfortunately, this is very unlikely in an astrophysical setting, actually, for this particular effect to happen. So then we went to the case that you have spinning particles, so taking some of the structure into account. I didn't mention, but this is pole-dipole approximation, of course, so no quadrupoles or so on involved here. Then you have some additional promising collision points that were related to this function C that could become zero in principle, but at least in all spacetimes that we checked, they are unphysical, so they are always behind the horizon, and they mark points where the force velocity becomes superluminous. So these are not very promising, actually. So, and then I explained to you this collision close to the horizon setup, but there then you have the problem that you somehow need to create this near critical particle with, in general, very small energies living very close to the event horizon. So this is some also not very nice points, but maybe one can exploit this a little bit farther. For example, for Hawking radiation or multiple collisions or whatever. And just let me point out these two papers. If you're interested, you can find more details there. And thank you very much for your attention. I hope I am in time.
22 minutes. So,
Oh,
but
sorry.
it's okay, but it's no matter. But it's excellent talk. But unfortunately, we have time for only one question due to these circumstances. So I do not see. You could raise your hand and or unmute yourself and ask question. Two ways. I apologize, Eva, but it's
fine.
no,
then we save some time.
No questions, but 22 minutes, but no matter. Thank you very much. Please stop sharing your screen. Yes, next speaker is Professor Oleg Zaslavsky. Please. Yes, good. Start sharing your screen. 17 minutes for talk and 3 minutes for questions and discussion. Okay, good. Yes,
Do you hear me?
Please, full screen mode. Oleg, please. Full screen.
How to make it?
No, but you have some full screen. Yes. Снизу. Экранчик снизу. No, правее мышку. Правее. Вот здесь. Где экран?
Что-то не вижу.
Ну, нижняя панель, там, где экран.
Да.
Ну, там экран, вот на экран нажмите.
Это может быть максимум, больше
Нет,
не получается.
экран, нет. Full screen мод. Или...
Sorry. Oh.
Yes,
Okay.
Good. Go ahead.
Yes. Okay. First of all, I thank the organizers for possibility to deliver this talk. The subject of my talk is overlap of two different effects relevant for high energy collisions. This is some new phase of the Penrose process and the so-called Barnard's silk vest effect of particle collisions near black holes. As we know, the Penrose process consists in the possibility to obtain debris of collision with energy higher than initial input. And this is achieved if time component of the metric coefficient change its sign. Meanwhile, some another modification of the Penrose process attracts attention during last decade. It is collisional Penrose process. It turned out that from the point of efficiency, it is much better, or maybe not much, but is anyway is better than standard Penrose process. And it plays a crucial role in the effect of BSV effect, about which Eva made her nice talk. This effect, in some sense, supplies us with acceleration of particles for free. There is no necessity to invest money to build accelerators. And in this context, there are two key quantities. First of all, this is the energy of the center of mass frame, which can grow unbounded in this effect. And also there is another quantity. This is energy, killing energy of debris at infinity. And one may ask whether or not this energy also grow unbounded. If yes, by definition, the corresponding effect is called super Penrose processes. And one reservation is in order. We work in test particle approximation, so let us leave, put aside the question about how these high energy processes affect the original metric. So we are faced with two energies. And what is the relation between both? In principle, there are some universal relations derived by world, which restrict the value of particles due to decay or collision. And calculations on the basis of this inequality shows that typically, if some massive particle decays, the efficiency is of order 35%. So it gives something, but not very large. And there is also a modification of this equality for massless case. And again, there is some finite, but more or less moderate gain in energy. Collisional Penrose process consists in that two particles collide and create two new particles. In this case, we'll see that efficiency may be significantly higher. First of all, when we ask how to apply the world inequalities in this case, is very easy. Two particles that collide in one point can be thought of as some combined particle of the effective mass m0, and the role of the mass is played by the energy in the center of mass frame. With some minor modification, we can apply the world inequalities again. The most important point that one can infer from the application of world inequalities to a particle collision consists in the following. If we are faced with the process that has finite mu, so finite energy in center of mass frame, the energy or frequency, if in the massless case, of new particle cannot be unbounded. It is also finite. So if we want to obtain unbounded energy, the necessary but not sufficient condition consists in the unbounded mu, energy in the mass frame. And in this context, we can rely on the Pcb effect, where indeed, for some circumstances, this quantity is unbounded. So we have this reaction in and we are interested in the condition on energy E. It turned out that in the black hole case, so when particles collide near the black hole, the effective centrifugal barrier around black holes prevents us from reaching unbounded energies and at infinity. The situation can be somewhat improved in the Schnittmann scenario. I remind you, first of all, that as Eva explained us, in the original scenario of Banana Silk West, two particles fall from infinity towards the black hole in the same direction. But Schnittmann considered a modification of this scenario when one of initial particles goes from the horizon. This is quite possible for near critical particles. And as a result, the efficiency grows by this numeric factor. but nonetheless, it remains finite. Formally, one can consider a collision of two usual, not critical particles and obtain formally infinite enhancement. But the problem is that usual particle cannot come from the horizon of a black hole. This situation corresponds rather to a white hole, and this situation is quite exotic. I will not discuss it further. There are also some other objects, which in particular wormholes. And Krasnikov showed that if particles move from opposite mouth of the wormhole, and this wormhole is very close to the formation of a black hole, then the energy in the center of mass frame indeed can become unbounded. But with some reservations that one cannot simply take the limit of the black hole, since in this case, the Kachman scalar grows as well, so we obtain the singularity. But some intermediate cases are possible. In this Krasnikov scenario gives us unbounded energy in the CM frame, center of mass frame. But if we ask about the super Penrose process, what happens? Literally, in the Schwarzschild-like wormholes, this is impossible because any Penrose process, super or standard, requires negative energies. In the Schwarzschild metric or some Schwarzschild-like wormholes, there are no negative energy. So super Penrose process is impossible. But as we know, in the rotating space-time, the negative energy in general appear. And it turns out that answer is positive. So for collisions near wormholes, rotating wormholes, super Penrose process is also possible. Also, we can consider collisions when there is no horizon, but there is some singularity, and particles reflect from the potential barriers which surrounds in singularities, say in the Kerr metric, and collide with new particle coming from infinity. In this case, also, it turns out that the answer is positive, and not only energy in the center of mass frame, but also energy at infinity can grow unbounded. In a sense, we can somehow view at this process formally. Every process for collision near black hole or almost near black holes when the horizon is on the verge of forming but doesn't form, it has some trademark. It is dependence of the energy on the lapse function. And it turns out that we can classify different processes according to this dependence, more exactly asymptotic of this dependence for small n, and count all physically relevant objects and see when the super Penrose process is possible or not. And here you see the table for collisions of neutral particles. You see that typically the answer is no. But there is exception in the second line. Then this process is possible. Up to now, I discussed processes with pure neutral particles, but there is also charge counterpart. First of all, even much before the particle collision issue, the Nardo-Ruffini noticed that there exists some analog of Penrose process in the case of static but electrically charged black holes. And this gives idea to apply this issue to the charged black holes and check whether or not super Penrose process is possible. It turns out that for, say, radial motion of particles, there is no potential barrier, there is no obstacle to reaching high energies, and the super Penrose process is indeed possible. To achieve this process, we must take some near-critical particle where deviation of criticality has the order of the lapsing function. Here C is some constant, and dependence on the sign of content of this is constant, and initial direction of motion, one can find 4 types of scenario, and typically they contain such scenario for which there is no upper bound on energy. Also, you can take another version for particles moving not in the equatorial place, but along the axis of the, say, Kerr-Newman black hole, and the results are similar. So let us return to simple Penrose process in the charged background. One more interesting property of this setup consists in that it admits limiting transition to the flat case. We can send gravitational constant to 0, and the black hole disappears, but what is important, generalized ergo-agent remains. First, this was noticed by Dadic, and as a result, we have high energy processes with no black hole at all. Gravity disappears, but some imprints, but some Cheshire cat smile remains. And moreover, not only Penrose process, but also super Penrose process in space-time is possible. Roughly speaking, 2 particles collide, one of particles passes to the level with negative energy, and the other particle acquires some additional energy and escapes to infinity. So let me repeat the table and say how it's modified for the for the charge case. All no for the table in the neutral case are replaced by yes in the charge case. Moreover, even such situation is possible when energy in the center of mass frame is finite, but energy at infinity is unbounded. One can ask how it can happen and how to reconcile it with the world inequality. The answer is simple. The world inequalities contains relevant combination as is written here. And finite X is compatible with large formally unbounded energy E and Q. And this is effect, this is some reminiscent of the Schwinger effect quantum field theory, but differs from it because there is no classical limit here for Schwinger effect, some known locality and so on. In our case, the situation is much simpler, and the scenario can be local. And there is one more issue which I would like to dwell upon. This is super Penrose process for
Excuse me,
non-extremal
Oleg,
black hole.
excuse me, sorry for interruption. You used 18 minutes at the moment. 18.
Okay, I'm going to the end. For non-extremal black holes, there are some prejudices because of which people deny the possibility of the BS effect, but it turns out that it is indeed possible, and energy in the center of mass frame can be unbounded, and energy at infinity can be unbounded as well. But in this case, energy is unbounded, but the mass should be unbounded. This is some specific feature of this effect in the non-extremal case. So conclusions. For rotating objects and collisions of neutral particle, we constructed full classification of relation between properties of energy in the center of mass frame and behavior at infinity. It means the connection between BSV effect and SPP effect. This includes collision in singularities near rotating wormholes. And there is counterpart of this effect when there is no rotation with the electric charge, and the electric charge favors the Penrose process. And even in flat space-time, a pure eclectic case, no rotation, the effect is possible. Thank you very much.
Thank you very much. Thank you very much. It's we have time for only one short question and short answer, please.
Well, looking for any acceleration process is very important. But if you put some matter outside the black hole, you have other processes to consider. Did you do that? The other point is charged black holes. I'm an old friend with Ruffini. So, but you know, if you have a little bit of charged particles, you get charge neutrality very quickly. Is it worth
the central point of the BSV effect consists in the presence of the horizon of a black hole, or some analogs for singularities and wormholes. So it is not very important, is it horizon of a black hole surrounded by matter, or some idealized Kerr or Reshner-Nordstrom black hole. So in this sense, yes, the effects survive.
Actually, probably some supplement to your comment. So, of course, in astronomical conditions, it's very hard to imagine that you have significant charge. But in last period, people suggested appearance of Reissner-Nordstrom metric in tidal charge due to extra dimensions. Also, it was 20 years ago, it was Dadich et al. Paper. And also, let us say, some versions of Hardetsky theory. They say they also could derive Reissner-Nordstrom metric due to interaction of scalar and tensor fields. Of course, it looks, at the moment, it looks like exotic, let us say, versions for appearance of Reissner-Nordstrom, but there are no, astronomical constraints on these parameters. Probably for you, it's also suitable because practically you are considering metric. So, but appearance of metric is not important for you, as I understood.
Yes, and in the last paper, I mentioned briefly the tidal charge as well.
Okay.
Right.
If there are no other questions, let us thank speaker again. And please stop sharing your screen, Oleg. Yes, you did it probably. And next talk, stop sharing your screen.
Как это сделать?
Наверху. Красная кнопка. Red button at the top of your screen. Stop sharing your screen.
Все.
Okay, good.
Yes.
So next speaker should be Nathan Late about cows, but he wanted to ask some of his co-author. Who is this person?
It's me.
It's
Can
me.
you hear me?
Good. Alessandro, please share in your screen. And you have 17 minutes for talk and 3 minutes for questions and discussion.
Thank you very much.
Okay, go ahead.
So I will present this work of many Nathan Lee and also undergraduate students from the University of Concepcion, Hugo Parchesky and Gustavo Ceballos. I'm also involved in this work. And anyway, these are Nathan's slides that I will present. And anyway, this work was mainly done by undergraduate students. So the main topic of this talk is the chaos in the Cartesian three-body problem, and which is one of the most ancient problems in physics. And of course, there is no analytical solution to it. And what is the main interest? Oh, it doesn't go. Can you have to change the slide? Okay, the main interest from the astrophysical point of view in the three-body problem is nowadays due to gravitational waves. In fact, I show you here in this left this figure. This is a global cluster of stars, 47 TAC, and the density of stars in the center of this star cluster is so high that stellar collisions can happen every few million years. And when two stars get together, by chance, they can start having a very chaotic interaction, gravitational interaction that is schematized here in this, you can see here this trajectory. In this case, there is a binary, so a bound single body that interacts with a third body here. You can see the chaotic trajectories, and as we know, this unstable, non-hierarchical three-body problem doesn't have any periodic solution or stable solution, except a few cases. So this system is bound to break up into a binary and a single, as you can see here. And specifically in this case, the body 1 and 2 enter as a binary, but the 1 and 3 exit as a binary. So this means that during this interaction, there was an exchange between two particles. And this kind of interaction can be schematized in this pseudo Feynman diagram here. You can see from this paper, from the 83 paper of Hutt. So this is in the specific how simulation of kind of such interaction looks like. Okay, I need to start like this. So this is a visualization from Aaron Geller of Northwestern University. You can see here a single black hole in this case coming from the distance, then interacting with this binary. There is a small exchange in the middle, and then again further chaotic interaction in which, for example, there is a temporary state in which the triple is in hierarchical state. There is a faraway binary and a single, but then they are bound to come back together because the energy between the binary and the single is still negative. And so after a few chaotic interaction, the system again will end up as a single and the binary. And usually it's the least massive object that is ejected from the interaction. And that's also what statistical theory have been trying to predict. What is the branching ratio of the three-body problem of the ejected particle based on the relative masses. So as you see, the three-body problem is extremely chaotic, which means that in the Lyapunov sense, you can change the initial position of the particles, initial velocities, and the system will behave in a completely different way at some point. And probably is best shown from this kind of plot here. So this is another three-body instance of the three-body problem. In this case, 3-point masses are at rest, and then they start interacting. So you can see here, this is the distance from the center of mass of each of the particles as a function of time. But here, actually, initially, it's not possible to see that this plot includes several systems with very small perturbation in the initial positions. And this starts to appear later on. And after a few after six crossing times, is a time scale of the system to evolve, you can see that chaos has already made the trajectories to diverge. And so the initial very small perturbation between the trajectories has been amplified, and the trajectory are diverging. This is in essence chaos, and it's also sometimes is referred as the butterfly effect. And the Tripoli problem is one of the simplest instances in which we can study chaos in the analytical system. Okay. Sorry. So if now we can imagine a scattering experiment in which we start with a binary, we make him interact with a single object, and then there is a interaction. We can maybe set up the system in a way to reduce our degrees of freedom to only 2. And in this case, our 2 degrees of freedom are the initial phase of the binary, or true anomaly in the language of classical or celestial mechanics. The phase of the binary, we can go from 0 to pi, and also the inclination of respect of the single with respect to the binary plane, for example. So if we set up the system like this, so we pick up the masses of these 1, 2, 3 bodies. We pick up the major axis of this binary. We keep the eccentricity with 0. We can kind of study. We can vary the different inclination and binary phases, and so explore the initial phase space of this Tripoli problem, which will be only limited to 2 angles: the inclination from 0 to pi and the binary phase. So, so this is what happens when we run, for example, several Tripoli simulations. So in this is the phase space of our system, initial phase space. Here is the inclination in the y-axis, and the binary phase at the x-axis. And each of these dots is a single simulation. And we have run with very high precision integrator that I wrote personally. And so what you can see here, the colors represent which particle got ejected from the system. And each color, green, red, or blue, represent a different particle. You can see that from in this phase space plot, 2 neighboring points means 2 initial conditions that are very, very close by. And well, faraway points are kind of initial conditions that are not very similar. But basically, we can see that there are very regular islands in this phase space plot, which means that if we perturb a bit the initial conditions in this, for example, in this blue island, we always end up with the same macroscopic outcome. So the ejection of the blue particle. Same for these green, these 2 green islands. So you can see that from this initial phase space plot, this is a kind of, we can use it as a metric to describe chaos and the sensitivity to the initial condition of the Tripoli problem. So what happens here, that we can clearly see that this initial phase space is divided into regular regions and chaotic regions in which the balloon is truly chaotic. Okay. Okay. So this was an experiment that we studied in the classical sense in the paper by Village and undergraduate student from the University of Chicago. And then we moved on, studied a different initial setup, which is called the so-called equilateral triangle. So in this case, we have 3 equal mass point masses and particles, and that lie on an equilateral triangle. And if they are at rest, have 0 velocity. So if we release them from rest and evolve the system, they will collide at the center of mass in a three-body collision, truly a mathematical collision. However, in this case, we don't simply take the unperturbed system, but we slightly perturb the position of each particle in a neighborhood of the vertex of the triangle. And then we evolve the system. So in this case, we can perturb this initial configuration and study what is the outcome. And what I will show you next is another phase space plot, but in this case, we show the ratio of the edges of the perturbed triangle. So you can see these S1, S2, S3. These are the length between the perturbed triangle that is formed by the 3 particles after we perturb them from the perfect equilateral position. And this is how it looks like. So again, each of these points represents a single simulation. Individual simulation here, there are probably 10 million of these kind of simulations. And we can see that this phase space is also divided into chaotic regions, which if we slightly change the edges of the triangle, we obtain a completely different macroscopic outcome. And some other regions in which the three-body problem is quite regular. And all this work was done by Hugo and Gustavo, the 2 undergraduate students. So you can see that we are actually even able by employing some kind of metrics to understand, to evaluate the degree of chaotic and chaos in your problem. We can even separate the two behaviors. So we can extract a regular subset from the whole ensemble of realizations and a chaotic subset here. And you can see that this phase space is clearly fractal. You can see the fractal distribution in both plots. You can see as we, for example, in this figure here, as we put one of the binary very far from the single, then we have some repeating pattern down to 0, only due to the symmetry of our problem, which there is a binary which is quite very far from the single body. But you can clearly see that this regular subset, which is clearly non-chaotic, extend down to the singularity here, where the three-body collision in the unperturbed problem would occur. And if we kind of zoom in on the singularity, we see that indeed, the smaller the perturbation to our particles, the more non-chaotic or regular the system behaves. And at the end, we reach, by diminishing the size of our perturbation to the position of the particles, eventually we reach a moment, a resolution in which you can clearly see there is no chaos anymore. The phase space is clearly divided into 6 areas in which, by perturbing the system, we simply obtain always the same result, and there is no even chaotic boundary between these 2 regions in which a particle gets ejected. So, of course, so this is quite interesting behavior of the two-body problem. But of course, this is only classical. So we're not considering any general relativity correction that we can apply to the equation of motion, the Newtonian equation of motion. And this is what so if we suppose that this particle represent black holes, we can actually introduce some corrections to the Newtonian equation of motion by employing the so-called post-Newtonian expansion. So in this way, we treat general relativity correction as a perturbation, the classical equation of motion, and we can evolve again the system. And in this case, what happens is that there will be gravitational wave radiation, and therefore merging between two black holes. And this also means that our system becomes scale-free, not anymore scale-free, but we set a physical scale to the problem, or the body problem.
Excuse me, Alessandro.
Yes.
You used 18 minutes.
Okay.
How many?
I'm just very. I think I'm very close to the end.
Okay.
So you can. Yeah. So you can see that we can kind of lose the resolution, and close to the singularity we obtain lots of collisions. And we also did another kind of experiment by using the triangular equilateral initial configuration. So this is actually a an unstable solution of the two-body problem. So if we slightly perturb the position of each particle, the system will collapse again. We will break up eventually, and we repeat the same phase-space plot, and we see that the system is kind of even more puzzling, and the rotation appears somehow also in the chaotic in the phase-space plot, and we still can separate chaos from we can still separate chaos from the regular subset. And okay, so after we run these simulations and we study the system from a classical point of view, what can we actually do with these experiments? And if we want to kind of extrapolate, for example, we know that if our perturbation go below the Planck length, then our classical simulations are not actually valid anymore. So how can we, rather than showing the conclusion, the main idea of this talk was to kind of open some debate on how to use these experiments as a way to think about how we can extrapolate or imagine our classical system in a more realistic setting. Okay, so this is it. I think Nathan also wanted to advertise his book on celestial mechanics and computational astrophysics. You can find here. But okay, I will finish now.
Okay, thank you very much for interesting talk. Three-body problem is one of the most important problem. I mean, for centuries. It's not final solution of this problem, but anyway, unfortunately, we have no time for questions. But if there is some urgent question, so please ask only one. If not, let us speak again. Next speaker is Professor Yuan Ha. He is here or not? I do not see him in the list of participants. If there are no, he did not come, but in this case, last talk of this session will be delivered by Alfredo Herrera Oguelar. Please go ahead. Are you here? Okay,
Yes.
good. Yes. Do you have camera?
Yes,
It would be better to show your video also.
sure.
Okay, good. Go ahead. 17 minutes for talk and 3 minutes for question.
Thank you. Hello to everybody. I would like to present a work done in collaboration with Ulises Nucamendi, Raúl Lizardo Castro, and Omar López Cruz, which is related to the gravitational redshift detection in a galaxy, in a black hole supermassive, in a supermassive black hole galaxy. As an example, we take the NGC 4258 active galactic nucleus. I would like to thank the organizers as well for allowing us to present this talk in the 16th Marcel Grossman meeting. And I will give a rough plan, starting with a brief motivation, and then I will show how the parameters of a black hole in the center of a galaxy can be modeled using geodesic movement of massive and massless particles, and using as well some conserved quantities. And then we use the redshift in order to infer these parameters, as well as some orbital parameters. And we will try to apply the method to the black hole mass of NGC 4258. So our interest is to develop a general relativistic method to detect general relativistic effects, in particular the gravitational redshift generated by a black hole. And then this method will allow us to estimate black hole mass. And in the most optimistic scenario, we will be able to set something about the spin, which has been elusive in most of the methods applied so far to black hole or supermassive black hole galactic nuclei. So the far end of this method is to apply this, to apply the method to this set of S0 stars, which is revolving around the center of the Milky Way. And because of the quite general kind of orbits we have in this system, we will try to start with the simplest one, with the circular and equatorial case, which is one of the simplest ones we can realize, but in fact, we have some astrophysical systems that have this geometry. So here we have a picture of NGC 4258. There is an accretion disk in which there are several clouds of water masers which are emitting towards the Earth. And actually we see the system edge on, which is one of the conditions we have to apply for the simplest geometrical case I was talking about. And then, since we have several astrophysical observations that point to the evidence that in the center of any galaxy we have a supermassive black hole, and from GR we know that these black holes are characterized by the mass and the spin. Space-time curves in the presence of a black hole, and the objects moving around it perceive this information codified in it. They dynamically fill the magnitude of the black hole, mass, and the spin. So we would like to use the redshift and the blue shifts of photons emitted by massive bodies like stars, masers, or gas orbiting around the black hole. And these photons shall travel along null geodesics in order to reach the Earth and be detected. And we will use also some orbital parameters of these revolving bodies. So here we present the Kerr metric. And then we will characterize the movement of the stars around the black hole with the four velocity. I would like to emphasize that the UT component of the 4 velocity is not present in the Newtonian formalism. This 4 velocity is normalized in general relativity. And since we have for a Kerr metric 2 Killing vectors, we have 2 conserved quantities which are related to the energy and angular momentum of the particle moving around the black hole. And we have also a Carter constant, which we represent with the letter Q, capital Q. So it is known that for this system, we can get an expression for all of the components of the 4 velocity in terms of the metric and the black hole parameters and the conserved quantities as well. The same can be done for photons, for massless particles moving around the black hole or in the vicinity of the black hole. And then we have the expressions for the 4 momenta of these photons. And with the photons and the components of the 4 velocities and the components of the 4 momentum, we can construct the frequency of these photons at the moment of the emission and at the moment of detection. And with this the redshift expressions will follow. In fact, we can define it as it is shown here. We have also the light bending parameter, which is preserved along the whole photons path, which is defined in this way. And for the Kerr metric or for the axial symmetric metric, we have this expression. And for the Kerr one in particular, we have this one. So here we have a sketch of the model. We have the observer located very far away. In an ideal situation, the observer will be static. We have the black hole and several massive bodies orbiting around it, which are emitting photons towards the distant observer. And these photons will be redshifted or blue shifted. And with the aid of this blue shift and red shift and the positions, I mean, there's some astrometry information, the position of the massive bodies which are revolving around the black hole, we will be able to extract information about the mass and also the spin of this black hole. So in the case of equatorial and circular orbits, the total redshift, the total expression I showed before, is this one, gets very simplified. And we can extract by definition, if the distant observer is static, this component can be set to 0. And then the gravitational redshift, the expression for UT, the UT component can be expressed in this way, defining the gravitational redshift. And the second component of this, the second term of this expression will define the kinematic redshift in this way. So the gravitational redshift is generated by the presence of the black hole mass, but there is also some dragging due to the rotation of the black hole. And these two quantities make the total redshift completely asymmetric in comparison with a Keplerian approach in which the kinematic redshift is symmetric. So the idea is if we have Z1 and Z2, the redshift and the blue shift for photons emitted by these orbiting bodies, they are functions of the orbital parameters and the black hole parameters as well. So the idea is to invert this problem and to get M and A in terms of the orbital parameters and the redshift and the blue shift. So the expression for the total redshift when the observer is very distant is this one. And we see that it contains information about the position of the massive particle, M and A. So in the case of Schwarzschild, when we drop the spin of the black hole, we have this expression for the total redshift, this expression for the gravitational redshift, and this one for the kinematic redshift. We see in blue that this expression, if we perform an expansion, the leading term in this total redshift will be given by the kinematic redshift, which is the expression that usually is employed in Keplerian dynamics. And the first correction is the one which is shown in blue, and this is the gravitational redshift. So if we take into account that the black hole can be moving from us or toward us, we must take also into account the systemic velocity of this dynamical system, the black hole with the accretion disk or with some stars. And then we will also could take into account the inclination angle of the disk with respect to the equatorial plane, given by this θ0. So if we consider the case of NGC 4258, which consists of a central supermassive black hole with an accretion disk in which there are several clouds of molecules of water, which are emitting in an assisted or in an assisted way towards the stimulated way towards the Earth. Yes, here is the Earth is in this direction. So there are 2 points in which the photons will be redshifted, and here the photons will be blue shifted. There is also some information about the photons which are systemic, but we will not need them in order to employ or to apply our method. So here is the observer, and we will use the masers which are red-shifted and blue-shifted from these points, for the points of maximal emission. And by using the model I presented, we will have to rely on a Bayesian estimation in order to get the black hole mass parameter, which in this case is about 4 times 10 to the 7 solar masses. The total redshift expressed in terms of velocities will be the systemic velocity plus minus 19 kilometers per second. So these masers or these molecules of water are revolving very fast around the black hole. And the systemic velocity is estimated to be of 483 kilometers per second. we, at the beginning, we tried to fit the black hole mass, the black hole spin parameter as well, but there is no sensibility so far in order to determine the rotation parameter. And we use some priors, the distance to the Earth given by the paper Wright et al., and as well as the inclination disk polar angle of 82 degrees reported by Herstein et al. So if we compare during this study the GR and the Newtonian rotation curves and the residuals, we see that both approaches are very close. Here GR is the red line and the dot orange line is the Newtonian one. This rotation curve tells us that both models are very close to each other when fitting the data. So we try to get some information about the gravitational redshift, which in this case is about is less than 1% of the total effect, in the sense that if we take into account the maximum redshift for the closest to the black hole maser is about 9 kilometers per second. But we saw before that we are talking about 900 kilometers per second in the movement of the maximal emission for the redshifted masers. So this effect of 1% is not detectable at the moment because the error in this data is still big. So let me conclude. We have presented a GR method for estimating both M and A black hole parameters and using the redshift emitted by photons, the redshift of photons emitted by massive particles and their orbital data. The total redshift encodes information about the Doppler velocity, the gravitational redshift, and also about the gravitational dragging. And we can consider as well the systemic redshift. We made a new estimate for the supermassive black hole mass in NGC 4258. But however, when we try to get information about the gravitational redshift and see if it was detected in this system, we saw that the errors that we have so far in the data prevents an ambiguous detection of this general relativistic effect. A generalization of this approach can be implemented to detect try to detect the gravitational redshift effect in the set of S0 stars revolving around Sagittarius A star. And further precision both in redshifts and star positions is needed in order for the method to be successful when estimating the mass of a black hole and probably the spin. Thank you very much for your attention.
Thank you very much. We have, thank you very much for interesting talk and perfect timing. We have time for questions, if there are any. So I do not see rise. Oh, okay, Stanislav, please.
Thank you for interesting talk. I would like to ask a question. In a final version of your method for obtaining parameters of motion, do you use full general relativity or only take into account certain terms of redshift in powers of 1 per R?
Yes, thank you. We take the full expression. Actually, We don't need the expansion in terms of M over R in order to estimate. The Bayesian fit can be used for the full expression of the total redshift. And then we estimate the mass with the help of the full expression.
But can you ask what is the formula for redshift that you use? Because in the slide you saw any formula that use only terms that correspond to general relativistic only approximation to general relativity.
Is this one?
You slide this.
This expression is full, is complete. This here we have added the systemic velocity of the galaxy as a whole in a Newtonian way, but we can also compose the redshift in terms of a special relativistic redshift plus the general relativistic one in order to get this total redshift. But this expression is very close and very fair in the sense that it's a very good approximation. But the total redshift is this one.
And this is only true for circular orbits, if I understand.
Yes. In order to get that, we are working in developing the general case for orbits of for eccentric and off the equatorial plane cases, but we have not arrived at the final result so far.
Yes, thank you for the answer.
Okay, I also have a question. So it's in some sense, it looks like a generalization of Andy Fabian idea to evaluate, let us say, mass and spin from shape of iron K alpha, X-ray iron K alpha line. But also I understood that you could evaluate mass inside orbit. But how did you distinguish extended mass distribution inside orbit and the mass of, let us say, black hole? Because it's, I think it's with this technique, it's not distinguishable.
No, it's not. We can't distinguish because what we take into account is the gravitational field generated by the mass. But
yes,
we don't
exactly.
about the distribution of the mass distribution of the central body.
But if you are speaking about mass of black hole, you say you have to extract mass of that is extended mass, which is inside this your orbit, because you said that this black hole mass is this one. So
yes, this is related to the first assumption we did. We are modeling the black hole with the Kerr metric, and as far as we do this, we are supposing that the particles are moving in the gravitational field of this Kerr metric, and then the distribution is hidden in this assumption.
Yes, it's hidden, but it's it has to be extended mass distribution because you're observing these objects.
Do you know a method in order to take into account the mass distribution for?
Probably yes, because who knows? Because it's probably some typical, because there are some models. Because you need, let us say, black hole metric, not very far from black hole in, let us say, position. But if you are far away, it's simply you could use Newtonian mechanics. But even in this case, you have, let us say, redshift and let's say blue shift. It's Newtonian mechanics. You have it.
Yes, when we are far from the event horizon, both of the metrics coincide.
Yes, exactly, because you also show that is Newtonian metric for location of let us say these masers or sources far away is the same. For Kerr metric, for Newtonian metric is if let us say million of Schwarzschild radii, so it's the same. Simply the same.
But even for the system we consider, this gravitational redshift is of the order of 9 kilometers per second in the vicinity of for the closest to the black hole maser. So it's not still detectable unambiguously, but it's already computable and probably detectable in the near future.
Also, some reminding. I remember that from major sources, Martin Rees evaluated mass of black hole at the galactic center as 5 million solar masses almost 40 years ago. So, but it's a rather precise estimate. So sometimes people could evaluate rather precisely.
What is precise is the spectroscopy. What is not precise, the spectroscopy. What is not precise is the astrometry. The positions of the stars, of the masers around the black hole are still very, very high. I mean, the errors in these positions are still very, very high, and they infer some error also in the redshift, because there is no error from the observations, from the observational data for the redshift. So we must infer the errors from the positions of the stars. So as far as the position of the stars have a high or a large error, then the method is not so effective.
I agree.
So we need more precision in the positions of the stars in order to be able to detect the effect.
I agree. Thank you very much. Professor Yuan Ha did not come. Okay, no response. In this case, I would like to thank all speakers of the session and all people in the audience for listening. And thank you very much. We are closing the session. Thank you very much again.
Alexander, before we close,
yes,
I checked again. When you put a vertical magnetic field, which is nearly stationary, over larger scale distances that we talked about, the theory works.
Okay.
So
thank you very much. I have to think about this, this message, because it's for you it's very easy to deal with magnetic fields, but for me, but always I have to think. Thank you very much.
Another question related to, in your opinion, to the previous speaker. Yes. There is an experiment made by Magic. I forgot about concerning a massive black hole. Suppose, like he says, 10 to the 7.
Yes, yes.
The partial radius is enormous. In the old time, when we consider masses, the order of the sun, in the old time, it was a microscopic distance. Now, they argued with their experiment that they could see phenomena over scale distances smaller than that radius.
It's
an enormous distance. So it could be plasma floating above this region. What do you think about that?
Sorry, I didn't understand. Some matter revolving at a distance smaller than the Schwarzschild radius?
Right. There is it's published in Nature. In fact, the principal author, what is he's speaking at this conference. I meant to say it's a philosophical question. What is your opinion of that?
Well, we can get information about any source which is behind the event horizon, right? And we know that for the Schwarzschild black hole, the smallest stable orbit should be of 6m, of the order of 3 Schwarzschild radii.
Right.
So I don't know, maybe this is pointing out to
very big microscopic distances.
Yes. Maybe this is pointing out to the fact that this is not a black hole, that the black hole is not the correct metric to describe this this system, and or maybe that
well, you can see it on Nature if you're interested. But
you say magic, right?
The magic experiment. In fact, the main author is a friend now. I'm sleepy. He's participating in this conference.
Do you remember his family name?
Probably Mirzayan or not. Mirzayan. Agaranyan from Magic or not.
Yeah, also he's from Magic. He's another person. It doesn't matter. But you can see it in Science magazine published.
Science of nature.
No, he's science.
Science.
Okay. Okay, thank you very much for also interesting remarks. Okay, okay. See you, see you, see you. Bye. We are closing the session. Thank you very much.
Bye-bye.
Bye, bye. Thank you.